What's up guys, and welcome to a new tutorial. In this video, as you can see, we're gonna do a bird strike simulation. I know that I've did one before, but this one gonna be a bit more detailed, and I will cover things that I did not cover in the previous video. So the first thing that's gonna be different is the turbine will be a bit more detailed, and the second part is that the turbine gonna be deformable material. So in my first video, the turbine was rigid material. So with that being said, let's start doing the simulation. So first I will mesh the IGS file of this guy. So here I open the prepost, then I go to import IGS, then I go import geometry. So sorry, it's not here, and I think this one. This file was provided by a friend of mine. So if you want a similar file, you can just search online. You'll find many of them, especially in the GrabCAD website. So specify the units here. I want things to be in meter. Okay, just wait for it. Okay, now I have the turbine and I have the bird here, this shape which represent the bird. As you noticed before, I said I specify the units and I make it in meters. When you do the pre-processing, you need always to be aware of the units. So in this video, I'm going to use the standard SI units. So my length will be in meter, and later I'm going to insert the density. So I will use kilogram, and the velocity and everything I use meter per second. Alright, so we go back here. Now how to mesh this? First I mesh, auto measure. Just click on this one, constant size. Then I can click from here. Okay, solid 1 is turbine, solid 2 is the bird. So I click on this one, then compute. You will see this is the size, the recommended size. Of course you can make it smaller, but for the time being I will try with the recommended size. Okay, and you see this is my mesh. So here I click on accept. Okay, as you can see here, auto measure tool always generate shell mesh, but the geometry is solid here. I mean the CAD file is a solid file. As you can see here, we have one shell outside, one line and one line. I will explain that more. I go here and then blank tools, and then I blank, meaning hide some of the elements. You can see now, if I click here, you can see the blade has 2 layers, which is actually not correct. See, it has 2 layers. I better do like this, make it clearer. You can see it has 2 layers. That's why the mesh right now is not very accurate. So what we can do, we need to make solid. Okay, why I want to make it solid? Because the thickness is not constant for the blades. You can see here at the side is a bit thinner, and in the middle it's a bit thicker. That's why I have to make, or I better make, solid mesh. If I want to make it with the shell mesh, then the thickness will be constant, which will not be accurate. So now to make this one a solid mesh, first I go to here, I hide the shell, then I display this one. Okay, you can see here we have shape group, FEM parts. FEM parts is the geometry after you mesh it. Of course here it's imported from the CAD from the CAD software, it has only surfaces. It does not have any elements, so the simulation will be performed on these guys, the FEM parts, not on the shape group. But we need a shape group in order to generate the mesh. So I go to the mesh, tetrahedron mesh, then pick skin part or skin geometry. I pick the skin geometry because I will use this one. I can pick here or I can click here. Then element size, it was around this, I think. Click on the try mesh. You can see now you have a solid mesh tetrahedron. And then I'm not sure if the size is okay or too big, but let's try first. First I click on this one. This will create the surface tetrahedron shell. Then I click on this one. It will create a tetrahedron solid. Okay, now it's overlapping because we are seeing the FEM parts and also we are seeing the solid one, the geometry. So I hide this one. Now you can see I have only the FEM part. Okay, so you can see here new part from tetrahedron measure. So here I go again. I want to show you that here we have a solid elements instead of shell. Here now if you can see, if I hide this, I have elements. I have like a solid inside. It's not void like before. So I unblank all. Okay, now this one is shell. I don't want it anymore, so I just right click, delete. And this solid one, I already mesh it, so right click and delete. Then I have a solid here. This is the one that represent the, what we call it, represent the bird. And here I have the turbine. Okay, now I do the same step on this guy. This one will be made out of SPH particles because they can handle the deformation much better. So for that, first I make a surface. I mesh the whole thing like this, the whole bird. Compute the size. Okay, mesh. I think the size is a bit too rough, so I can make it, let's say 10. Okay, this is acceptable. So now I hide the solid. I have, this is my shell, the one that I made just now. So I want to convert this one to SPH. So go down here, SPH generation, then shell volume. Okay, then click on this shell, and then the density of the bird material. The density gonna be in kilogram per meter cube. And for this one, I'm taking the density from this paper. Okay, this paper by Dr. Ozair, one of my friends. You can see here he used the bird. This is the material for the bird. Okay, so you can search for other papers to find different material properties, but in this video I'm using this one. So here is 950 the density, kilogram per meter cube, which is our units that we are using. That's cool. So I go here, I put this one 920, click on set parameters. Okay, nothing is generated. Why? Because the XYZ is very big. It's 1 meter and this guy is less than 1 meter. So let's say I put like this and see if I have any particles inside. Set the parameters again and create. Now you can see here control and the middle mouse, you can see we have some particles inside. I want to increase the distance between particles because I don't want the simulation to take a long time. This is, I think, just make it 20 mm. Okay, the density, let me check again. 950. This density is 950. Reject here. Set parameters. Create. Now I have this mesh. Then accept. Okay. Now again, I hide the FEM parts. I show this solid. Okay, I don't want it anymore. So right click and delete. Yes, delete. So now I have my parts. Okay, I have the blue parts and I have the green part which I don't need, and I have the SPH which gonna be my bird material. So I right click on the part 3, the shell, and delete because I don't want it. Okay, then F2, click on F2. I show everything. Okay. Oh wait, things are disappearing. Okay, now I want to change the view of the SPH. I can go from here, general setting, SPH, make it just 4. It become sharper. It's okay. This is only how to represent the parts. Okay, now as you can see here, the bird is very far away from the turbine. So it's better to make it close here to the turbine, because otherwise it will just make the simulation longer and waste our time. So I go to translate and then click select by part, and then I want to go in Z direction. Let's say I put 10 mm is too slow. 0.1 meters. Okay, this is good. Okay, now it's close enough. Accept. Okay, now next, I want to go to measure. Then let's say I view top, view from the top view. Click on here. Wait. Click on right on the nose. Okay, this is the coordinate of the nodes. Okay, X, Y, Z. Why I want to measure this one? Because I want this one to be in the center. Because if the axis of rotation doesn't go through the 0, 0, 0, then we will need to define the axis of rotation. So instead of defining the axis of rotation, I move everything to the center. I go to transfer, I go to transform, translate, then XYZ, I put the coordinate just now, then I click on everything whole and translate negative. Okay, accept. Now if I measure again the tip of the nose here, you can see is very close to 0, and I think that should be enough, because this one again, this coordinate e to minus 6 is like just typically it's just 0. Okay, now before I move next, I want to define a shell inside here. Okay, so I go to mesh. I do it first, then I'll explain why. Generate, element generate, and then go to shell. You can make solid or shell, but here I'll just make shell. And then solid surface, click by element, pick and propagate, then click on the inner surface here. You can increase the angle. Okay, I think not this one. Sorry, element, solid face. Okay, now create, accept. Although it's not visible, but here I have this inside, you can call it hub. Why I need this one? This one because the part gonna be rotating, that's why I will assign the rotation, the angular rotation of the turbine to this part, and this one is already fixed with this one, so they will rotate together. So I think that's all for the meshing. I want to go to keyword. First I go to part. What is part? I just want to make them 1, 2, 3. So this one SPH node, I make it number 3, and this one number 1. This step is not really necessary, but I like it to be 1, 2, 3, because I know that 1 is red, 2 is blue, and green is 3. So if I make it like this, then I can tell easily which part is number 1 and which one is number 2 and which one is number 3. And it's also a good practice to name all the parts. So this one, part number 1, the red one, is the inner hub. Part number 2 is the blue part. This one is turbine. And part 3 is the SPH particles, which will be my bird material. Accept. Okay, now I want to define the section. I can actually define straight away from here. Okay, so section, click on this dot, then new keyword, then from here, this one, hub section. So it can be any thickness, but it's always possible to, it's always better to make it very small thickness. Accept. Okay, now the turbine, the material of the turbine is solid, so I make a new keyword, then new solid. We can just stay with solid number 1. If you want more detail, you can scroll down here and go to number 13, I think. Number 12 or 13, or you can even go higher elements, but higher order elements, but the default one is enough, so accept. Then lastly, the bird is SPH, so section, new keyword, and then SPH new, then here SPH particle or SPH section, then accept. Okay, why this thing is necessary? Because we need to tell the software which is the type of the section. For example, here when I define the shell thickness of the hub, I needed to input the thickness of the shell, because shell is two-dimensional elements. That's why we need to define the thickness in the defined section. And for the solid, we need to define the solid type, because we have different type of solid. Sometimes you have the pentahedron elements, sometimes you have the brick elements, which is the common elements. That's why we need to define the section for the solid parts. And for the SPH here, we need to define the SPH particle, we need to define the section as SPH, because they are different type of particle method. Not only the SPH, we have like the SPG and other methods which also use the particles instead of the mesh elements. Okay, so now we are done with the section. Next we go to what we call it material. Okay, the material I can define from here, but I also can define from part here like I did with the section. I can just click here, okay, new keyword, or I can go here and then select select the material type that I want. So now I want to define from here, so it will be already linked, or I will just define there. So I use different ways in this video. So first section, the right one, this one is the hub, it's gonna be rigid one, new, and then this one hub. The density, let's say this one is steel. This is the density of the steel, and the Young modulus is 200 gigapascal, Poisson's ratio 0.3. Then accept. Okay, why I make this one rigid? Because it's easier to control the constraint of the rigid material. So this red one gonna be allowed to move, rotate in the Z axis only. So I control that from here, this one and this one. So I put number 1, constraint applying global direction, and then constraint, okay, this is the translational constraint, I put it 7. This guy should not be able to move in any direction, it should be only allowed to rotate in Z. And this is constraint 2, so should be equal to 4, because it's allowed to rotate in X and Y. Sorry, it should be equal to 4 because it's fixed in the X and Y rotation, but it's allowed to move or rotate. It's allowed to rotate in the Z direction, so it should be equal to 4. Accept. So after I define here, I go back again to part, and then I link it here like this, and then done. Okay, now the next material is gonna be the material for the turbine. So the material for the turbine gonna be Johnson Cook. Okay, and this guy should be aluminum. Okay, what is this Johnson Cook material model? If you open here, okay, this is the Johnson Cook material, it's a quite famous one, and this is the equation that relates, or this is the flow stress equation in Johnson Cook. Why I'm using this material model? Because in this material model we have the effect of the plastic strain, and we have also the effect of the strain rate, and we have also the effect of the temperature. But in our problem we don't actually need the effect of the temperature. But this birdstrike is gonna be a dynamic problem, and the strain rate is very high, and when the strain rate is high, this will affect the material properties, and that's explained with this epsilon dot here, which is the strain rate, which control the strain rate, or which influence the strain rate in this material model. So we go back here. So I will just put the material properties of this guy. So now that I put the input parameters, this is the density, shear modulus, Young modulus, Poisson ratio, viscoplastic, rate effect. I put it 1, and then I put A, B, and C, and M. These guys here, A, B, N, and C, and then this M is this one is for the temperature, and then this is melting temperature, the room temperature, the reference strain rate, heat, specific heat, and this D1, D2, D3, D4, D5 is the damage parameters. And I think that's all. Accept, then done. Okay, now before I go and link that to the turbine, I need to define one more thing, which is the equation of state. So equation of state, linear polynomial, I put it number 2 because this part is part number 2, but if I put here 1, it's also fine, as long as you link it correctly to part number 2 in the part definition. So this one, EOS for turbine. Equation of state relates between the density and the pressure, and you don't always need to define it all the times, but in our case we are using the Johnson-Cook material model and we are using it with solid elements. That's why we need to define the equation of state. And in this case, everything will be 0 except the parameter C1, which will be equal to the bulk modulus of the material. Here, and accept, and that's done. Now that's done for the turbine. So collapse all, so model only part, and then the inner hub is defined. It was the easiest one. The turbine, the section, I need to define it. I already defined it, solid. The material is the aluminum, Johnson-Cook material model. Equation of state is this one, and then accept, done. Alright, now we are done with the turbine. Now we go with the SPH, part number 3. So go to all, and then material. Some references use the null material, which is 009, but in the paper that I'm referring to, they are using this material, which is elastic plastic hydro. New material number 3. Here will be bird material. I can refer to this paper here. So this is the density. This is the shear modulus, 2 gigapascal. And the Young modulus is 0.02 megapascal. Okay, this is 2 gigapascal, the shear modulus, so it should be 2 e to the 9th, and then this one 0.02 megapascal, so it should be e to the 6th, and then I think accept. Then here you can see they also define equation of state. So I need to go again to that guy, equation of state, and define it for the bird material. So a bird material, and then I have C1 is 2.1. C1 is 2.1 gigapascal to the power of 9, and then here 6.2, and then 10.1. Then accept. Okay, so now I go to part, bird, I link this bird material and I link this equation of state, then accept, and okay, need to save before everything crash. So browse, can put anywhere, but here I should save it as keyword file. So here birdstrike .k, and then save. Okay, so we define everything. Now we need to define the interaction between the bird and the turbine. Okay, the interaction between the hub and the turbine, no need to define it because they are already fixed together. How come they are fixed together? Because we made this hub material, this hub mesh from the turbine itself, so they are already fixed. So we need to define now only the interaction between these two guys, and that's done using contact. So here, contact automatic node to surface. Double click this one and then new ID. Here I call it bird to turbine. Okay, nodes to surface. So nodes should be the slave, master should be the surface because it's node to surface. I will define the part first. The master type gonna be number 3 because I will define the bird here. Sorry, this should be the turbine. And then as for the bird material, this one should be number 4, node set. Okay, so I put here number 4. I don't have a node set defined yet, so I click on this one and it will give you this reminder. So you create this one from new entity. Then here I go and say I put this number 3 because this is part 3. I can put any number here, doesn't matter, but that's my practice because this part number 3, I also like the part set to be number 3. And then here I say bird node set, then select by part and select on this one. See, all of them are selected, then apply. Okay, and that's all what we need. Okay, we can define the friction 0.3, 0.2, here also 0.3. Okay, this is the friction, the static, this is a dynamic, and this is the exponential decay. This one need to be defined, otherwise the dynamic friction will not give any effect. So that's complete the definition of the contact. I click on accept. Then done. Okay, so the contact is defined now. Okay, I go to set. This is my set node. Okay, I click, it will show. I unclick again, it will hide. See the contact. I click on this one, it will highlight the guys. If I unclick, it will remove the highlight. I can do here remove the mesh to see it. See, no, still not enough. Okay, now I'm showing only the edge. So here you can see everything is highlighted. When I click on this one, I click again, it will remove the highlight. Okay, so this is an easy way to see if our definition of the contact is correct or not. Alright, now I need to define the initial conditions, which is the velocity of the bird and the rotation of the turbine. So I'll go to all, then initial velocity generation. Okay, here first I want to move the bird, or first I want to rotate the inner hub. Sorry, first I want to rotate the outer hub. So this one will be slave, the set type will be number 2 because it's part, and we have turbine. And then what is the velocity? The velocity, I'll just make it 200 is a rotational velocity, so it should be omega. Okay, so omega, I think I will define it as 200. This 200 means 200 meter per radian. Okay, sorry, this 200 will means radian per second. Angle is always measured in radian. And this, we just make it 1 because it will rotate around the z-axis. So this one is 1. Oh, sorry, not here. This actually is the rotation axis. But our rotate, because if you remember, we remove everything to the global 0, 0, 0. So we don't need to define these guys. We only need to define either one of these. So here I put 1 because our rotation is around the z-axis. Then accept and then done. Okay, now this one will be moving. Again, initial velocity generation, new ID. Now I put this one number 3 and the direction is minus 120. There is no rotation, only minus 120 for the bird, part number 3. This one we remove it, no need, then accept. Okay, now I define the initial, I define the velocity of this one, and also I define the rotation, but this one is only initial velocity, meaning the velocity is only applied at the start. But actually we want this one to keep rotating, and what keep the turbine rotating is the inside hub here. So we want this one to be always we want the inside hub to be always rotating at a fixed angular velocity. So that is defined by a boundary condition. The initial velocity, the initial angular velocity of this turbine will be only applied at the beginning of the simulation. Then this bird material will hit the turbine and might make the increase, it might increase or decrease the velocity of the turbine. If this one is very heavy, then it will damage the turbine or it will stop the turbine, depends on the material. So the turbine velocity is not constant. That's why we define it using initial velocity. But the inside hub here always will be kept rotating at a fixed velocity. So boundary prescribed motion rigid, because if you remember we defined this one as rigid. Part ID inner hub, new here, hub rotation, degree of freedom gonna be number 7. Okay, rotational degree of freedom, VAD is whether we want to define the velocity, the acceleration or displacement. So here just make it 0 because we will define the velocity. And this is the curve, load curve ID. We need to define a curve which relates between the velocity against time. So here we don't have any curve defined yet, so I click on this one, this will pop out, new keyword, and then curve is already here. Sorry, no, it's not here yet. You need to click this one, new curve, and then angular velocity. Okay, at time equal to 0, the velocity is constant 200. Insert. When time is 10, also the velocity is the same. Angular velocity is same, is 200 radian per second. Okay, then accept. Done. Okay, so now we define almost everything. Okay, So I go to I have two more things, I think. Two more things. First, the control, which I accidentally click on model check, not yet. Collapse all, go to control, scroll down here, SPH. Okay, here I put not 4, this one I put 2 equal to 3. This one will be automatically changed to 3 if you are using the new solvers, but if you are using a old version of LS-DYNA, then it will give you an error. But if the new version, it will just give you a warning and just change it to 3. Why 3? Because we have 3D problem. Okay, and here click on accept. Now go to time step, the scale factor, I will make it 6. You can leave it as default, but for safety I just make it equal to 6. And then termination time, let me see the size of the file. Size of the file is only 4 megabytes. So if that's okay, then from my experience, if you put 10, it will be fine. It will not take much long time because the file is only 4 megabytes. Okay, now the control command is done. Now we need to define the database. The database is actually the output. What are the output that we want? So the basic thing is here, D3 plot is to plot how many frames. So you can here control the intervals between the output. So the smaller the DT, the more smooth your animation will be, or you can decide just here, okay, number of plots. So if you put, let's say 100, then it will divide the end time into 100 and will give you 100 outputs. Okay, and this is also, it's not available in the very old versions of LS-DYNA. So in our case, I have the end time is 10. So if my end time is 10, so here I put 0.1, then accept, done. That's the basic. I can go for some extra output here, ASCII options. The interval also 0.1, and then what I want here. Here the boundary condition, forces and energy. An important thing here is the reaction forces, the resultant interface forces. It will measure the force between the turbine and the bird material. And I think that's enough. Accept and done, and Control and S to save the file. The file is already saved, so I copy here. I will run it. Pause. Okay, so now before I run, I want to check actually if my file is okay or not. Go to model check and then go to keyword check. Oh, there is one error. Good that we noticed that. See here, what is the error? Okay, so it says because we are using tetrahedron, then we need to use 4, 10 or 3, or use E sort equal to 1. I think this one should be only a warning, not an error. Let us try. Here I put 8 processors for this simulation, although that the laptop doesn't have 8 processors in the memory allocation. I put 1000 million. Run. So wait, if it shows you the time, then everything is okay. If not, it will give you a termination error and tells you what is the problem. Of course, it might take some time because I'm using this on a laptop, and also I'm recording this video. This too much time because a mistake in the time, but not because of the file being so big. Control, I click on Control C, click, it will stop here. Then I put SW2. Okay, you see it, the time changes, but still a lot because my time is not accurate. Control C and again now I put SW1, it will stop. Okay, the mistake is actually because the time we agreed the time is in second, not in milliseconds. So when I put the termination time here, it should be 0.01. Now it's accurate. Done. Now the database, I need to change these guys too. So 1, 2, accept. Then DT plot, I have this one, P minus 3. Okay. And Control S. Then I open this one again, the LS-DYNA manager. Then I click on this one, run the analysis, the last analysis. Then I click on OK. Okay, now it will take 1 hour. I try to click on Control CSW2. Yeah, it must be that there is something quite not accurate. Otherwise, this one should not be very high value. It might be that some of the properties in the material is not accurate. So for section solid, should be number 10. Accept. Because it's a tetrahedron. So now I will try to rerun this one again. And let's hope things are okay. Okay, now it will take only 34 seconds. 34 minutes. And this makes sense now. With a file size of like 4 megabytes, and the termination time is 10 milliseconds, then this is acceptable time. If it is too much, then there might be something wrong. So now I Control C SW2. Now it will say only 9 minutes. So I want to check whether things are okay or not. Yeah, things seems to be moving. Never mind this one. This is the last frame is just a mistake from the previous run, because in the previous run we did not change the element type of the what we call it of this guy, of the turbine. That's why all these things are happening. Okay, but so far things seem so good, and it seems like yay, it's hitting and separating. So just we have to close this one and be patient for 5 minutes. Okay, so I think we can view the results now. This is just the number the line number in the output file, because when you run this one, when you run any simulation, it will produce a message file at the end, and this one is just the number of the line in that file. This one is the time of the simulation. Okay, so when this one reach 10 milliseconds or 0.01, then it will finish. This is the time step. The smaller the time step, the longer it will take, and it just report to you like at this time there is D3 plot file has been produced, and this is the date and this is the time. Okay, 4:45:09 seconds AM. Open from here. It will open the last simulation that you run. So here you can see it's moving, and then it's splitting and hitting the turbine. And you can see it hits again here. Everything is cool. Okay, what else you can hide this one, the mesh, French component, the contour plots. You can see here, this is the plastic strain of this guy. You can see here also there is a plastic strain. When you move here, you see at this moment there is some plastic strain, and the reason why, because here it starts the reason here why, because we have the rotation of the hub and we have the rotation of the what we call it, the turbine, the blades. Okay, the rotation of the inside hub is constant, but the rotation of the what we call it, of the turbine is only at time equal to 0. That's why we have this very small strain. I click on F2. I try to hide this guy, the bird. Now you can see now the strain is more. But you can see it's more spread, but the value still is very small here. Now French component. Now here you see the stress. You can see the bird is getting hit. Okay, I go to setting again. Post setting. Oh, not post setting. Setting, general setting, and then the SPH. This is smooth. Can make it point. You see, become point. You can even make it surface. So now you can see the SPH is surface. Click on view here. Now it is like a surface, but when it is split it won't be that nice. You will not be able to see the split here in this case if you view using the surface style. So the best way is smooth. In my opinion, the best way is smooth. You can control the size of the particles, make it bigger or smaller. This is too small. So it's almost done, but we can close this one and open again to see more frames. But we know now that the results are fine, and the bird is moving and hitting the blades, and everything is good. Yeah. So you can see here. show it in the perspective style so it's more nice. So that's all for this tutorial. Thank you very much for watching. If you like this video, just give me a thumb up and don't forget to subscribe to my channel. See you next time.